Okay. Okay, so thanks to Giovanna, Rosa, Graham, and Juan for Roberta, sorry. Sorry, Roberta, Rosa, Graham, and Juan for organizing this workshop and for giving me the opportunity to present this talk. It is based on ongoing work with Sonja Petrovic and Dane Wilburn. And the main purpose of this talk is simply to raise some questions, which in my opinion are interesting and worth being investigated, but haven't been studied much so far as I know. And please correct me if you know results afterwards, or let me know. All right, so let's start by fixing some notation. We want, throughout the talk, S will be a polynomial ring in n variables over a field, and to keep things simple, we'll assume the characteristic of the field is 0. I will be always a homogeneous ideal. I call it Artinian, meaning the quotient will, S mod I, has codimension 0. And in this setup, one can ask the questions many of you have asked and studied. Has the quotient A equal S mod A the weak Lefschetz property? And thanks to Alexandra, I don't need to define this anymore because she took care of it. And if you prefer the strong Lefschetz property, you may as well ask it for the strong Lefschetz property or some weaker version or related version of the Lefschetz properties. Maybe some comments are in order. If you have at most 2 variables, the weak Lefschetz property will always hold. Yeah, so in this talk, I will stick to the weak Lefschetz property. If you have at least 3 variables, we are counterexamples, so it won't be always true. On the other hand, we know many interesting classes of algebras which do have the weak Lefschetz property. Tomorrow we will actually hear some talks about recent progress. If you came to the last meeting last fall in Cortona, there was a whole series of talk about the proofs of the G theorem and generalizations. So we know very interesting classes of algebras which do have the weak Lefschetz property. Moreover, if you like to experiment, if you choose the generators of your ideal I randomly, say using Macaulay 2, I would expect the resulting algebra has the weak Lefschetz property. In fact, more generally, if you present me an algebra, most of the time I would expect this to be the algebra to have the weak Lefschetz property. Now, most of the time is not a mathematical statement. And so if you are more open-minded, you may simply ask, well, how likely is it that A has the weak Lefschetz property? Well, of course, this is a vague question, intentionally so. Nevertheless, I'd like to see answers, plural. The first step would be to turn this question actually into a precise question. And there are several ways to do so. In the talk, I will focus on just one option. And this is modeled along the lines of one of the early successes of probabilistic methods in combinatorics, more generally, more specifically about a framework for studying large graphs. All right, so, and this goes back to Erdős and Rainey. They proposed the following model to study graphs. So as your vertex set of the graph, you fix the numbers, the integers from 1 to n. and then you fix a real number p strictly between 0 and 1. And p, well, it's between 0 and 1, so it's supposed to be a probability. So what you do now, you form a graph G of p and n by connecting any two vertices in your set from 1 to n randomly with probability p. You chose with constant p, you connect to pick any two vertices, connect them with probability p, independently from any other possible edge or non-edge. Once you're done, you got a graph. And this is with G depending on P and N. Maybe just for sanity, right? You have N choose two possible edges. You choose each edge with probability P. So you expect that your resulting graph has N choose 2 times P edges. Any questions so far? All right, well, so we want to use this model, but now to get a better sense what's happening typically, we will vary N, the vertex size of our graph. But if we vary the vertex size, we should also vary P, because if P is constant, P will drop out playing a role. So we vary the vertex size and make P dependent on the vertex size. And then we consider what happens if N approaches infinity. And in this regard, Erdős and Renyi established the following striking result. So if the product of the vertex size and this probability P is less than 1, then the graph you get will almost surely have no connected component with more than log n vertices. And if I say more than log n, it's about the order of log n as n approaches infinity. On the other hand, if the product is 1, then the graph almost surely will have a connected component, a largest connected component, with about n to the power 2/3 vertices. If the probability for I think it's, yeah, it's O. Oh. Yeah. I thought so, yeah. I mean, I hope I looked it up correctly. I mean, anyway, I mean, what there's a much larger, I mean, the largest component has much more vertices than in case A. Yeah, but that's. What is almost surely? Yeah. Okay. Yeah. So I wanted to state this in the least possible technical terms. So what was? I mean, this is. Well, let me hold back a minute. Let me wrote out part C first. If you increase the probability of P, I mean the P itself, then the graph will almost surely have a unique largest component with about n squared vertices. And so this is what's often called the giant component of the graph that you get if n times P is greater than 1, and no other component will have more than of the order log n vertices. And almost surely we'll have, well, so secretly you let n go to infinity and ask what's the probability that there is a connected component with more than this number of vertices, and this limit will be 0. This is what almost surely means. And of course, that's all a mouthful and rather technical, but intuitively, almost surely to me, this makes some sense, even if I don't know the details, and I hope it would do the trick. But yeah, I mean, what this demonstrates is clearly what's called a threshold behavior, right? The properties of the graph you get regarding connectedness change depending on the size of the product n times p. If it's less than 1, equal to 1, and greater than 1. 1 is a so-called threshold in this case. Okay? And now, what we want to do, we want to use this model as a blueprint to approach the question I started with in a special case, just to make things a little simpler, but there are many variations. So the special case I have in mind is you specify I to be a monomial ideal, and you want the quotient Artinian as before, but also level. Equivalently, that means, well, the socle of the quotient is generated by monomials of the same degree. Thankfully, Alexandra reminded us what the socle is, but there's another way I can define this from scratch. You could also say the ideal can be obtained in the following way. You pick a positive integer capital D, and then you look for monomials of degree D in your polynomial ring S. Choose a subset of these monomials, B, and then I is the annihilator of B, which means you take the intersection of the annihilators over all the monomials in B, and the annihilator of a monomial is just the complete intersection generated by these powers of the variable, where the exponent is 1 bigger than the exponent in the product. Right? And if B is empty, you set the annihilator to be the ideal generated by the maximum ideal. And maybe just one quick example: if you have 3 variables and you want to avoid indices, so I take x, y, z for the variables. I choose 2 monomials of degree 4. Then the ideal we get is just, well, the first monomial has this complete intersection as annihilator. This is the intersection for complete intersection for the second monomial, and out comes a monomial ideal with 4 generators. Right? Okay, but now we ask again our question: how likely has this monomial level algebra the weak Lefschetz property? Yeah, I should have said this in this. If I am in this setup, I will refer to the quotient as a monomial level algebra, just for shortness. Okay, now that still looks vague as before, but now we have seen how we could make this precise. So let's do this. So again, we will use sort of Erdős-Rényi type model to study these monomial level algebras. We fix D, let's make it at least 2 to avoid triviality. If the C is 1, it's not interesting. And then we want a subset of monomials in S of degree D. So we pick P, again a probability, P between 0 and 1, and P is the probability for picking one of the monomials of degree D in S. And then we form our subset B by including each of the monomials of degree S with probability P. That gives us a set B, and then we form S modulo the annihilator of B, and that's our monomial level algebra. And now we can ask precisely, now it makes sense in the mathematical, rigorously to ask, what is the probability that A has the weak Lefschetz property? Yeah.
So of course, if you chose the monomial xy, the cubic xy only doesn't take the ideal.
Oh, but I choose only the socle. So yeah, so I choose just in B. All the monomials have the same degree. But you're right. There's another model, and then it's, well, there are lots of variations, and maybe we can talk about this all in the question. I mean, I can say a little more about this. You're right. I mean, I just wanted to have this a simple case here to illustrate this approach for making sense of the question about how likely is the weak Lefschetz property. That's really the purpose of this talk. Now, I think this is actually a pretty difficult question to answer. But what we will do now is, as before, if we want a sense for what is happening typically, we will increase the monomials where we're looking for. And then, of course, we should again make the probability P for choosing an individual monomial depending on D, and let D approach infinity. And then we look, well, what happens? If you are very optimistic, you may ask, well, the probability that A has the weak Lefschetz property is 1 as D approaches infinity. That's, of course, the most optimistic scenario you could hope for. If you're a little more cautious, you may ask, well, are there thresholds, threshold functions, f of d and g of d, such that the probability that A has the weak Lefschetz property becomes 1 as D approaches infinity if P is much less than f of D or P is much bigger than G of D. And so what means much less? Well, the limit of P of D over f of D as D approaches infinity is 0, or analogously, P is much greater than G if the limit of G over P as D approaches infinity is 0. Right? So this is, in a sense, so, and of course, you should have in mind, if I write here less than f of D, P of D is greater than 0, or at least 0, and it's less or equal than 1. So near the boundaries, you could hope for at least you get something, you get the weak Lefschetz property, and in a sense, honestly, if I mean threshold, if you are very something in between, something different should possibly happen. There is some evidence that these, especially the second part, may have a positive answer. So let me spell this out. Namely, if the probability for P of D is at most n minus 1 factorial times D to the power negative n minus 1, then the probability for the weak Lefschetz property does indeed become 1 as D approaches infinity. But that is essentially for a trivial reason, because if P of D is that small, you will have picked in your B typically at most, you expect to have at most one monomial, then of course you get a monomial complete transaction that has the weak Lefschetz property. Similarly, if P is very close to 1, then one can also show that the probability for A having the weak Lefschetz property becomes 1 as D approaches infinity. Now, I will admit, I don't expect that these are the true threshold functions. I mean, I don't think these bounds are sharp, but it's just an indication there could be thresholds along these lines. Probably also worth recalling that one has to be careful. Not every level algebra has the weak Lefschetz property, and here are some explicit examples in the paper with Mats, Rosa, Juan, and Fabrizio Sanello. If n is even and the number of variables is even and capital N is at least 5, there's a specific example. You just choose again 2 monomials. And so they have a large common divisor, but then the resulting quotient does not have the weak Lefschetz property. All right, so this is just to say, I mean, of course, not every weak monomial level algebra has the weak Lefschetz property, so the best we could hope for is the probability become 1, if we are optimistic, or in certain cases we can guarantee that the probabilities become 1. Okay, now let me shift gears a little bit. It is certainly true, and many of you are probably aware of this, that the weak Lefschetz property applies that the H vector of the, or the Hilbert function of the algebra is unimodal. So it will increase, stays possibly flat, and will decrease. Okay, so let's look at this at the Hilbert function a little bit. And now, in the setup we have discussed, if you fix n the number of variables, d the degree of total monomials, and the probability for fixing a monomial of degree d in variables, then you can talk about what is the expected value for the Hilbert function of a monomial level algebra in a fixed degree, say j. Right? And then you record all the values of this Hilbert function, expected values of the Hilbert function in each degree in a vector, and this is what I will call the expected H vector, right? And then this is notation here, E of H1 indicates this is the expected Hilbert function in degree 1. That's not so interesting. This is the expected Hilbert function in degree 2, and so on. The expected value of the Hilbert function in degree 2. Mind you, it's not necessarily an integer, of course, right? It's an expected value. So, but what turns out to be true, that this expected H vector is log concave, which means in particular it is a unimodal. And just to specify what means log concave, if you look at the expected value of the Hilbert function in degree j, square it, this is at least as big as the expected value of the Hilbert function in degree j minus 1 times the degree of the expected value of the expected Hilbert value of the Hilbert function in degree j plus 1. So what has this to do with the weak Lefschetz property? Well, it's a very indirect, connection in the sense. What it says, at least this expected H vector does not present an obstacle to the possibility that the probability for the weak Lefschetz property having probability 1 as the d goes to infinity, that this is actually true. That you almost surely expect as d increases, your algebras have the weak Lefschetz property. This is the other way to saying it. If d increases, you almost surely expect A to have the weak Lefschetz property, which is the most optimistic scenario, but it's not impossible based on this result, which of course doesn't prove something, but it's an indication. At least the expected H vector has good properties. So we could hope for more. Well, I hope you find the type of questions I presented interesting. I would be glad to talk to you more if you are interested or have suggestions or results. And thank you for your attention.